Hi and welcome to day 31 of Just Start Programming, the Rust programming language. Our topic for today is the continuation of the Fundamentals of Asynchronous Programming, where we will cover working with any number of futures. So join me once again, live in one take, no shortcuts and no secrets. So let's just start programming. Okay, so yesterday we were doing this example from the Rust book, applying concurrency with async. Let's quickly go through just to refresh our memory. Okay, so this time it's using async. We're creating a new task with spawn task. So this is from the Rust programming language library spawn task. So we have to use this, we need to have the runtime. So from here, and then you have async. Inside the spawn task, you have this async scope as well. And then the output looks like this: line number 1, second, first, first, second, first, second, first, second, until it reaches 5 from the first task. Which one is the first task? No, it's not the first task, but it reaches 4 from the second task, mainly because here. Okay, so this is where we spawn. It's like spawning the thread. But over here, when it reaches 4, and then it stops. So you only get to see at most 5. Yeah. Version stops as soon as the for loop in the body of the main async block finishes. Okay, so this one, the result, we also unwrap it after awaiting. Wait. Updated version runs until both loop finishes. Okay, spawn task async, and then here you have handle await. So it's like similar to join. What's the difference between them? Okay, so here it looks like async and threads give us the same basic outcomes, just with different syntax. So instead of join, you can also make use of await, but in this case it's handle await. So over here you can also join two futures. So this one async will have a future. Okay, so it will wait for both. Now you'll see the exact same order every time, which is very different from what we saw with threads. That is because the RPL join function is fair, meaning it checks each feature equally often, alternating between them, and never lets one race ahead if the other is ready. So that's why you have first, second, first, second, first, second, first, second, and then finally the first task. The first task is the one with the, previously it was a thread, but this one will have 1 to 9, counting up on 2 tasks using message passing. What did we have here yesterday? So there's a tuple, sending it to the channel, the val, unwrap, and here you have the receive, await, unwrap. So here you can have multiple strings. This would be the multiple messages under a vector, and here we are iterating through the vector. So transmit, send the value in a vector, then it will sleep for 500 milliseconds. There's a wait. And here, while let sum. So let sum, what was the explanation here? Let else. Concise control flow with if let and let else. And where is let sum? Where was it? Let sum. It was not mentioned. No. Sorry, it's not let sum, but let with this value. So this one will return, what did it return? Some or none, which is option. Oh no, result. Was it result? Option. Okay. And then here another modification where you have two different async for this one and async for this one, and then you have a join, so it will consider both. Okay, the while let loop won't end until awaiting Rx receive produces none. Yesterday I think this one will continue to loop. It will continue on waiting. What's the solution again to make it stop? Okay, async move. Okay, so async move. When you run this version of the code, it shuts down gracefully after the last message is sent and received. So the move keyboard works with the async block, just as it does with closures. Okay. But if we could move transmit into that async block, it would drop once the block ends. This one. So if the block would end, transmit is dropped. Then this one, async channel, is also a multiple producer channels we can call clone. Okay, here from transmit can be cloned. Yeah, tx1 used here. So it's for this async block. And then tx, and you have another one here, tx future. This time it's using tx. This one is using the clone tx1. Okay. And here you will see all the messages from both ascending futures, and because ascending futures use a slightly different delays after sending, the message are also received at those different intervals. Okay, so this is a good start, but it limits us to just a handful of futures. 2 with join or 3 with join 3. Okay, so our next topic is working with any number of futures. Right. Working with any number of futures. When we switched from using 2 futures to 3 in the previous section, we also had to switch from using join to using join 3. It would be annoying to have to call a different function every time we change the number of futures we wanted to join. Happily, we have a macro form of join, to which we can pass an arbitrary number of arguments. It also handles awaiting the futures itself. Thus, we could rewrite the code from this thing 17-13 to use join exclamation mark. So it's a join macro instead of join 3. Then it will look like this. We can copy this part. You already know where to change it. So we have join 3, 1, 2, 3. So we can just place this from yesterday. And then this one here. So we didn't use, or we did not call await, because it says it will do that as well. It also handles awaiting the futures itself. Okay. This is definitely an improvement over swapping between join and join 3 and join 4 and so on. However, even this macro form only works when we know the number of futures ahead of time. In real world Rust, though, pushing futures into a collection and then waiting on some or all the futures of them to complete is a common pattern. Because here we have individual futures. 1, and then you have Rx and then Tx. But it was saying here that in real world Rust, you might be pushing futures into a collection, because the number of futures could dynamically increase and decrease. To check all the futures in some collection, we'll need to iterate over and join on all of them. The tprl join all function accepts any type that implements the iterator trait, which you learned about back in the iterator trait in the next method. Chapter 13, So it seems like just a ticket. Let's try putting our futures in a vector and replacing join with join all. Okay. So this one, I think we know what to do. That future. Where do we put that one? Okay, we can put it here at the top. So wrong. Okay. And then this one, join all futures await. Okay, so this one is explicitly calls await. I think join all doesn't handle await by itself. I mean, unlike this one. What is wrong with Rx? Where is Rx? Rx future mismatch expected async block. Consider pinning your async block and casting it into trait object. What is wrong with this? Async move. You have async move. Async. Can we put async move here? Okay, nothing happened. What is wrong? Mismatch types. 137.23 and 151.22. One 37. What's the error again? 137.23. No two async blocks, even if identical, have the same type. Consider pinning your async block and casting it to a trait object. Expected async block 137.23. This one, Okay, this one works. No problem. How about this one? This one works as well. This one. Futures. But where is futures? Does it work? Only two futures here. Oh, okay. Now there's an error. Then we uncomment this one. This one will have an error. I have no idea. Let's see. Oh, okay. So here. So it was expected. Sorry about that. It was expected. Okay, so this might be surprising after all. None of the async blocks returns anything, so each one produces a future output. Remember that future is a trait, though, and that the compiler creates a unique enum for each async block. You can't put two different handwritten structs in a vec. The same rule applies to the different enums generated by the compiler. To make this work, we need to use trait objects, just as we did in returning errors from the run function in chapter 12. We'll cover trait objects in detail in chapter 18. Okay, chapter 18. Using trait objects lets us treat each of the anonymous features produced by these types as the same type, because all of them implement a feature trait. Why is it an anonymous? Futures. What makes it anonymous? Future output. Okay, this one. So does it mean even if I only have two, I'll comment this out. Okay, then I'll remove this. That will still have an error. Okay, so nothing to do with this actually. It's just that output here is the same as the output here, the future type. Okay, then how do we fix it? Future trait. Note, in using enum to store multiple values in chapter 8, we discussed another way to include multiple types in vec, using an enum to represent each type that can appear in the vector. We can't do that here, though. For one thing, we have no way to name the different types because they are anonymous. For another, the reason we reach for a vector and join all in the first place was to be able to work with dynamic collection of futures, where we only care that they have the same output type. We start by wrapping each future in the vec in a box new, as shown in 17-16. Box box new, box new. Okay, box new. Then they will have the same uh, trait. Right. Future is a trait though, and the compiler creates a unique enum. Okay. Future is inside, it's being wrapped by box. Okay, so I think this one will still, okay, this code does not compile either. Unfortunately, this code still doesn't compile. In fact, we get the same basic error we got before for both the second and the third box new calls, as well as new errors referring to the unpin trait. We'll come back to the unpin errors in a moment. First, let's fix the type errors on the box new calls by explicitly annotating the type of the features. Okay, so features vector of box. What is this? And this one is something new. So we have to read the description below because this is something new. This type declaration is a little involved, so let's walk through it. The innermost type is the feature itself. Okay. We note explicitly that the output of the future is the unit type, parenthesis. By writing future output equals this. Then we annotate the trait with dyn to mark it as dynamic. Okay, so dyn is to mark it as dynamic. The entire trait reference is wrapped in a box. Finally, we state explicitly that futures is a vec containing this item. Vec containing this item. That already made a big difference. Now, when we run the compiler, we get only the errors mentioning unpin, although there are 3 of them. Their contents are very similar. That is a lot to digest, so let's pull it apart. The first part of the message tells us that the first async block does not implement the unpin. Okay, it doesn't implement the unpin. Unpin trait and suggest using pin macro or box pin to resolve it. Later in the chapter, we'll dig into a few more details about pin and unpin. For the moment, though, we can just follow the compiler's advice to get unstuck. In listing 17-18, we start by importing pin from stdpin. Next, we update the type annotation for futures with a pin wrapping each box. Oh, okay. So you have future, which is considered as dynamic, wrapped as box, and box as wrapped as pin. Finally, we use box pin to pin the futures themselves. Okay, so let's copy this one first. So we can uncomment. Where is it? Okay, here. Let futures vec pin box dynamic future. Okay, let's copy this. Can comment this out since that one cannot be used anyway. And we put it here. We compile and run this, we finally get the output we hoped for. Okay, so we don't have compilation error here anymore. And then join all futures await is here. This one I can run. Hi, more from the messages future for you. Okay, so that one compiled. And this one, yeah, so we almost have, yeah, I think we have identical output. Okay, there's a bit more to explore here. For one thing, using pin box T as a small amount of overhead from putting these features on the heap with box. Yeah, so box places the feature in the heap. And we're only doing that to get the types to line up. We don't actually need heap allocation after all. These features are local to this particular function as mentioned before. Pin is itself a wrapper type. So we can get the benefit of having a single type in vec. The original reason we can reach for box, not doing a heap allocation. We can use pin directly with each feature using the std pin macro. However, we must still be explicit about the type of the pin reference. Otherwise, Rust will still not know to interpret these dynamic trait objects, which is what we need them to be in vec. We therefore add pin to our list of imports from std_pin. Then we can pin, okay, this is pin macro, each feature when we define it and define features as a vec, containing pinned mutable references to the dynamic feature type, as in listing 17-19. Okay, so here we need to use this. I can add it here. Then text feature pin. Okay. Pin macro. Leave this one. So we can put it. Comment out this one. Okay. There's another error. Text one FUT. Text one FUT is here. Expected time, expected struct. Ah, okay. Okay. Yeah, because we did not do a pin. Where do we put the pin? Pin async move. Pin async move. So meaning pin should be here. Pin async move. And this one also pin. Okay, so I cannot put it there. It should be here. Oops. Okay, so no more errors. Let's see. We got this far by ignoring the fact that we might have different output types. Example in 17-20, the anonymous feature for a implements feature output was to U32. The anonymous feature for B implements feature object. Future output was at str. And then anonymous feature for C implements feature output bool. Okay, A, B, C. Okay. Let A result, B result, C result equals, okay, so this is a tuple, TRPL join A, B, and C. Print line A, B, and C. Okay. Can use TRPL join to await them because it allows us to pass in multiple future types and produces a tuple of those types. Cannot use TRPL join all because it requires all of the features pass into. Okay, so I think this is the limitation of join all. It requires all of the features passed into have the same type. Remember that error is what got us started on this adventure with pin. This is a fundamental trade-off. We can either deal with a dynamic number of features with join all as long as they all have the same type. Yeah, so join all can be used as long as they all have the same type. Or we can deal with a set of number of features with a join function or the join macro, even if they have different types. This is the same scenario with face when working with any other types in Rust. Features are not special, even though we have some nice syntax for working with them, and that's a good thing. Okay, let's verify first if this one compiles and if it runs. Could not compile. Where was it? Could not compile hello async due to previous error 3 warnings emitted. Pin What is wrong with pin? Error could not compile hello async due to previous error. 3 warnings emitted. A bit lost. Okay, let's analyze. Pin previous import of type pin here. Oh, pin is already in line 31. 31. And line 1. Can comment this out. Since pin is already here. Okay, that's the first one. Pin must be defined only once in the type namespace of this module. Okay, unused, unused, unused. Okay. I think this time we can compile. So it's building. Hi, more from the messages. Feature for you. Yeah, because of this and this one. Okay. Okay, so this is just for illustration. You can use trpl join macro to await them because it allows us to pass multiple future types and produces a tuple of those types. You cannot use join all because it requires all the futures passed in to have the same type. Remember that error is what got us started on this adventure with pin. Okay, this is a fundamental trade-off. You can either deal with dynamic number of features with join all as long as they have the same type, as long as they all have the same type. Or we can deal with a set of number of features with the join functions or the join macro, even if they have different types. This is the same scenario we'd face when working with any other types in Rust. Features are not special, even though we have some nice syntax for working with them, and that's a good thing. Okay, let's move on to raising futures. When we join futures, we join family of functions and macros. We require all of them to finish before we move on. Sometimes though, we only need some future from a set to finish before we move on. Kind of similar to raising one future against another. Raising futures is the topic. Okay. We once again use trpl raise to run two futures, slow and fast, against each other. So we have slow async. This one 100 milliseconds. This one is fast. This one has only 50 milliseconds. So that is half of this. And you have race, slow, and fast. Await. Okay. Each feature prints a message when it starts running, pauses for some amount of time by calling and awaiting sleep, and then prints another message when it finishes. Then we pass both slow, and fast to TRPL race and wait for one of them to finish. The outcome here isn't too surprising. Fast wins. Unlike when we used race back in our first sync program, we just ignore the either instance it returns here, because all of the interesting behavior happens in the body of async blocks. Notice that if you flip the order of the arguments to race, the order of the started messages changes, even though the fast feature always completes first. That's because the implementation of this particular race function is not fair. So when it's not fair, then you get different outcomes. It always runs the features passed in as arguments in the order in which they're passed. Other implementations are fair and will randomly choose which feature to call first, regardless of whether the implementation of race we're using is fair, though one of the features will run up to the first await in its body before another can take start. Sleep, 150, here race, slow, this one is race fast. Okay, recall from our first async program that each await point, Rust gives a runtime a chance to pause the task and switch to another one if the feature being awaited isn't ready. The inverse is also true. Rust only pauses async blocks and hands control back to a runtime at an awaiting point. Everything between await points is synchronous. That means if you do a bunch of work in the async block without an await point, that feature will block any other features from making progress. You may sometimes hear this referred to as one feature starving other features. In some cases, that may not be a big deal. However, if you are doing the same kind of expensive setup or long-running work, or if you have a feature that will keep doing some particular task immediately, you need to think about when and where to hand control back to. By the same token, if you have long running blocking operations, a sync can be a useful tool for providing ways for different parts of the program to relate to each other. But how would you hand control back to the runtime in those cases? Okay, how do we hand it back to runtime? Where's the runtime? Okay, runtime is here. Yielding control to the runtime. Let's simulate a long-running operation introduces a slow function. Okay, there's a slow function named stru64. Thread sleep duration from millisecond. This code uses std thread sleep instead of trpl sleep, so that calling slow will block the current thread for some number of milliseconds. Let me think. trpl sleep. Does it make some noise? So that calling slow will block the current thread for some number of milliseconds. Can use slow to stand in for real-world operations that are both long-running and blocking. Okay, so it looks like this is the one we need. Let's see. So in listing 17-23, we use slow to emulate doing this kind of CPU bound work in a pair of futures. So we have two async. Where's the slow? Slow, okay. Slow A, slow B. To begin each future, only hands control back. To begin, each future only hands control back to the runtime after carrying out a bunch of slow operations. If you do this code, you will see this output. Okay. Runtime after. Are there any changes? Async A, async B. Sleep, duration from millis. And you have a race. Slow operations. Okay, because of this. Then we copy this one and put it in our code. Function A. Function main. Okay. Slow. Okay, and then we comment out this one. Then copy this part. Okay, so now this one is using slow. Slow will have a sleep duration based on the ms parameter. Okay, and it will look like this, as with our earlier example. Maybe we run it first. Error, gonna compile sync. Okay, so we have so many errors. Okay, so we added slow. Can use slow to send in for real world operations. We use slow to emulate doing this kind of CPU bound work in pair of futures. Pair of futures. Uh, okay, so here we can do that directly using yield now function. So another thing added. Yield now. Okay. We replace all those sleep calls with yield now. This one is what? Run. This run. Copy this. And this one we comment out. On it. And this one we okay. This code is both clearer about the actual intent and can be significantly faster than using sleep. Because timers, such as the one used by sleep, often have limits on how granular they can be. The version of sleep we are using, for example, we always sleep for at least a millisecond, even if we pass it a duration of 1 nanosecond. Again, modern computers are fast. They can do a lot in 1 millisecond. You can try see this for yourself by setting up a little benchmark, such as the one in listing 17-26. This isn't an especially rigorous way to do performance testing, but it suffices to show the difference here. Okay. This one, what happened to this? Let's run this first. Let's see the output. Oh. Error. TRPL channel. Extern create TRPL. Either. X and RX equals TRPL channel. Let me see anything. Okay, this part there is a yield now, and in our code, slow and yield now. We also have it, but the error is here. Is extern create the RPL. This crate mostly just re-exports items from other crates. RPL channel. No, we didn't have transmit receive. Maybe that's why. Yeah, so that one fixed it. Because in here we did not use any transmit or receive. Okay, so let's run it once again. Okay, so warning, that should be fine. Oh, we did not print out anything. B finished. I should have seen this one, but it's not here. Did I miss anything? A, B. Okay, that's just how the example was created. Okay, let's not insist on fixing that. Let's move on to this one. Okay, benchmark. Okay, and here we copy this. Instant is another std time instant. Oops. Let's put it at the top. Okay. What will happen here? Sleep version finished after 1.15 seconds. Yield version finished after 0.0012 seconds. Okay, so what was needed here? Duration from nanos. You have start instant now. And then instant now is a start. Then you have async. Okay, let's read the explanation. Here we skip all the status printing past a 1 nanosecond duration to TRPL sleep. Here, 1 nanos from duration from nanos, 1 nanosecond, and it's being passed here in sleep. Then we run for 1000 iterations and see how long the future using TRPL sleep takes compared to the future TRPL yield now. The version with yield now is way faster. Sleep. Yield now empty. Says here yield now is way faster. I already changed the code. Okay, so it's already changed. Let's run it. Sleep version finished after 1.13, so it took longer for sleep version. But yield now is quite fast. What is the other trade-off when using yield now? Okay, so it's mainly our instant now async, then it's calling yield now. This means that async can be useful even for compute-bound tasks, depending on what else your program is doing, because it provides a useful tool for structuring the relationship between different parts of the program. This is a form of cooperative multitasking, where each feature has the power to determine when it holds over control via await points. Each feature therefore also has the responsibility to avoid blocking for too long. In some Rust-based embedded operating systems, this is the only kind of multitasking. In real-world code, you won't usually be alternating function calls, which await points on every line of code. While yielding control in this way is relatively inexpensive, it is not free. In many cases, trying to break up a compute-bound task might make it significantly slower. So sometimes it's better for overall performance to let an operation block briefly. What was it? It's better for overall performance to let an operation block briefly. Always measure to see what your code's actual performance bottlenecks are. The underlying dynamic is important to keep in mind though. If you are seeing a lot of work happening in serial, that you expect to happen concurrency. Okay, building our own async abstraction. We can also compose features together to create new patterns. For example, can build timeout function with async building blocks we already have. When we're done, the result will be another building block we could use to create still or more async abstractions. Okay, listing 17-27 shows how we would expect this timeout to work with a slow future. Let slow equals async. There's a sleep here for 100 milliseconds. I'll wait. Then slow. Okay, it's async. Returns I finished. Okay, then there's a match timeout. Let's think about the API for timeout. Timeout. It needs to be an async function itself, so we can await it. Not. They're not both. Okay. I think the scope of async is only here. I'm wondering because it says here it needs to be an async function itself, so we can await it. Its first parameter should be a future to run. Can make it generic to allow it to work with any future. Okay. Its second parameter will be the maximum time to wait. If we use a duration, that will make it easy to pass along to TRPL sleep. It should return a result if the future completes successfully. The result will be okay with the value produced by the future. If the timeout elapses first, the result will be ERR with the duration that the timeout waited for. Okay. Here you have timeout, async function. Future to try F. It's a future max time duration. Returns a result of F duration. This satisfies our goals for the types. Now let's think about the behavior we need. We want to raise the future passed in against the duration. We can use TRPL sleep to make a timer future from duration and use TRPL raise to run the timer with the future color passed in. We also know that raise is not fair. Polling arguments in the order which they're passed. Thus, we pass future to try to raise first, so it gets a chance to complete even max time. Is a very short duration. If future to try finishes first, future to try. If future to try finishes first, race will return left with the output from future to try. If the timer finishes first, race will return right with the timer's output off. Okay. Slow async, slow, and we finish. And here we have a slow duration. returns a timeout. Okay, message. Yeah, you can print the message here. Error duration. So this one, there's an error. Async timeout. Okay, this is the one from here. Let's see what's the difference now. Future to try max time duration, result output duration. Oh, this is already the end. Okay, let me see. Future to try succeeds, and we get left output. We run OK output. No, we return OK output. If the sleep timer elapses instead, and we get a right, this one, we ignore the parentheses with underscore and return error max item instead. With that, we have a working timeout built out of two other async helpers. If we run our code, it will print the failure mode after the timeout. Failed after 2 seconds. Because futures compose with other futures, you can build really powerful tools using smaller async building blocks. For example, you can use this same approach to combine timeouts with retries, and in turn use those with operations such as network calls, one of the examples from the beginning of the chapter. In practice, you usually work directly with async and await, and secondarily with functions and macros such as join all, raise, and so on. You only need to reach for pin now and again to use features with those APIs. We've now seen a number of ways to work with multiple features at the same time. Up next, we'll look at how we can work with the multiple features in a sequence over time with streams. Here are a couple of more things you might want to consider first. We used a vector with join all to wait for all of the features in some group to finish. How could you use a vector to process a group of features in sequence instead? What are the trade-offs of doing that? Take a look at features stream, features unordered type from the features crate. How would using it be different from using a vector? The question mark. Don't worry about the fact that it's from the stream part of the crate. It works just fine with any collection of books. Whew, that was not easy. Yeah, let's take a look at the next one. Still a long way to go. Stream futures in sequence. Okay, so that's the next topic. Futures, but in sequence. It's another long topic as well. Okay, so let's do that in the following day. Let's end here for now, and then hope to see you again in the next video. Thank you so much.